At one time, I had been an instructor at the Boeing's Commercial Training Division, and then later I was transferred to the Space Center. Now, everyone thinks the Space Center is really, really high tech. This was this guy here, a teletype. What I want to point out is that before I get into explaining various different things about, shall we say, gates, and I'm going to call them functions or devices. I'm going to avoid the word gate as much as possible. At this particular time, the circuits were PNP with -6 volts. And I looked at the manual, that is the training guide or the Q&A manual for extra class, and they talk about negative voltage. But the negative voltages that they talk about is totally wrong. I'll get into that later, but I just want to show you here that when I tried to go back and do some research, lo and behold, I couldn't even find it. I mean, I know the circuits, I worked with them. Anyhow, this guy here was paper tape. All right, let's go on to another one here. While I was at the Space Center, this is where they tested the lunar orbiter and also the moon buggy. However, these guys, look at the tires. Those are pneumatic tires. This was their practice rig. I never did find out for sure where they were doing this. Don't know whether it was Idaho, Utah, Nevada, I don't know where. But anyhow, these guys are really enjoying themselves, getting used to that rig, nice fenders there and all. However, this is the guy that's on the moon. So we had the largest space chamber in the world when I was there. And I was there when all these things were tested and before this guy went up and stayed on the moon. So it was really quite a privilege to see what was going on. Now, the lunar orbiter, I want you to see some, that's the camera door right there, and that's the camera. One of the things that we did, not only did we check these out in a space chamber, and by the way, the space chamber had liquid nitrogen in the coils all the way around. It also had a hood, which we called the solar hood. And that was so that we could simulate with this thing being out in space, where one side of it was freezing to death and the other side was being boiled alive with the sun. So that's what we did. We simulated all of that in the space chamber. There's also something else. All of this was pre-tested ahead of time. The area that I worked at the Space Center was analyzing telemetry data from a missile with liftoff and stage separation. So we'd know what to expect that these guys had to be subjected to as a payload on the Saturn missile. By the way, not everyone knows, but I happened to find out that during the vibration testing, this door fell off. So they had to resolve that problem, and then they went back to their testing again. We had shaker tables just outside the bay window that I had, where I could look down and see what was going on. And the space chamber itself is about 50 feet away from where I was. So I got to watch, but never got to get this, put my hands on any of this stuff here. All right, one other thing. Oh, going back to this guy here, you'll notice the little marks in here. Now these wheels are hollow, they're steel bands. If you look closer, you can see where these steel bands interlock. So this whole thing is totally hollow. So it only weighs just the steel bands themselves. What this cover is here that kind of keeps things together, I don't know. When they were testing this in the space chamber, the only problem they ran into was it blew one of the oil seals. So when I went by the space chamber one day, I saw guys in there cleaning it. They had 2 weeks of going in there and trying to clean this thing out. The oil evaporated and that is blew up, if you will, in space and coated all the walls. And they had such a really neat job trying to clean everything up. All right. The lunar orbiter actually was one of several. And what it did is it made passes around the moon to take pictures of the moon so that the astronauts, these guys here, could land where they wanted to. I happened to look by as I went by one of the rooms one day, and I looked in there, and by the time this guy here had taken pictures, we now had the modelers made a representative of the moon with all of its craters, the landing spot and everything. And they had a camera on a rail that as it approached the moon fixture that they had built, and so it could rotate slowly, they were actually able to position themselves theoretically around the moon with this camera and then spot the place where they were going to land. Now, there was a computer system on board, and as it turns out, not everybody knows that just before they did a touchdown, the computer for landing, shall I say, misbehaved. And fortunately, in the simulator that they had there at the center, they had practiced landing and doing a dead stick. Well, lo and behold, the one in control of landing did have to do a dead stick landing for about the last, I think it was 60 feet, but I don't know for sure. Any questions as we go? All right, the next thing I want to get into, and this really gets into the main consideration of everything here. When I was at the Space Center, we were doing our analysis of all the missile telemetry with analog systems. And fortunately for the Space Center there, they decided that as technology was just so rapidly advancing, personally, as I look back, I really feel very fortunate for what I was able to observe. It was just absolutely amazing as things were progressing, just at a breakneck speed. Well, this is what we had here. We had one of only 2 analog to digital converters in the world with 320,000 samples per second with an accuracy of plus or minus 2 millivolts over a range of -2 volts to +2 volts. And NASA had the other one. And by the way, ours had to be certified every so often because as we were digitizing the data for analysis, we had to certify that it was meeting certain standards. Okay, any questions as we go? By the way, I've had to make some changes on my website. This is not on my website yet, but it will be. All right, the next thing is that while I was at the Space Center, my main task with this brand new computer system that we had there, I was responsible for maintenance on the entire system. And I'm sure you realize that a computer, mainframe computer, is totally worthless without support peripherals. So what I was doing is I was writing diagnostics for the support peripherals. When I left in '73, I had left behind about 200 diagnostics that had various different ranges for all the different peripherals that we had. And also I found myself writing a couple of new operating systems for that new Sigma 2 mainframe computer. And this was all in machine code. So it was a steep road for me for a while to master this, but I did accomplish that. And all of the diagnostics were in machine code. The operating system that I wrote for this mainframe was to run my diagnostics, but I also wrote a program, maybe you guys would appreciate, to copy all of the operating system currently on that system mainframe onto a mag tape, so then I could load mine on. So I had to write an image program to do this, and then I turned around, ran the same image program to put all of this back on the mainframe so as nothing ever happened. The scientific data systems here was the 910. This particular computer was actually about a 3rd generation computer. It was all transistors, And what it did, it managed all the nitrogen, liquid nitrogen coils that were in the space chamber. It controlled the solar hood, but it also was very much tied into all the instrumentation. And there's some interesting stories on that. Okay, while I was doing all this, my supervisor came down and said, they want you back over in industrial training. And I said, what on earth for? He said, I think it has to do with the AWACS. Well, anyone that knows anything about the AWACS system, there have been some earlier experiments, but what happened is Boeing got the contract for this. Let me see if I've got it here. After Boeing was done with their system and Air Force took it over, it was called an E3. So Air Force called it an E3. Now, during the building of the AWACS, and I'm going to back up here just a little bit. Here's the AWACS sitting on the ground. When this was brand new and it wasn't turned over to the Air Force yet, digital logic, and by the way, this is 1968, I think, is about when this was, 9 at the most. And this dome up here, I used to think that the radar rotated in the dome, but no, I was wrong. The whole dome does rotate. And this band that's here is where the radar is. And I have a picture of that radar. What happened is the Westinghouse engineers were building all of this to get it ready to go. The prototype where Air Force or where Boeing had gotten the contract for it. And then suddenly they realized that this was really early in the game, and the technicians working with the engineers did not know squat about digital. There were no really good classes available for it. So what happened is, just to make a long story short, I was called back into the instructor division to teach the crew that was putting this together, the technicians that was putting this together. I had 2 weeks with each of the 3 shifts of crews. I had 2 weeks to take them from absolute zero to fluency. And when I mean fluency, I'm talking about beyond what was being taught in the colleges. I had 2 weeks, so it was a rush course. I had to be very, very careful on what I presented to make sure that they could understand it right off the bat and that they could remember it and then apply it as soon as they got back and working with the engineers again. In fact, these guys were able to recognize circuit, shall we say, data change information and such quicker than the Westinghouse engineers that they worked for. So they were very mum about that. But pretty soon, some of the engineers began to catch on and ask, how come you got that quicker than I did? And so little by little, they became a better working team. So anyhow, those techniques.
Hey, Dave.
Yeah, go
Dave,
ahead.
yeah, on that last picture, what was that lump on the side just in front of the words Air Force?
I think, let me go back here. Oh, this is the radar. Okay, I'll go back there and see. By the way, I did get to go on that bird. They gave me a tour. You're talking about this lump right here?
Yeah, that's right.
That's where the navigator sits. And so I have a picture of the cockpit, which I'll bring up here as well. I think actually that was a navigator right there. Give you an example. This was the cockpit. And if you'll notice, right about in here, that bench there, and that's about where the navigator sits. And I have a suspicion, I may be wrong because I couldn't ask, even though I had a security clearance, I couldn't ask too many questions. These guys were also limited in what they could be told. But there's a lot of stuff behind this. And I think that's the bump you're talking about. What's there? Don't know. Now, there's one more thing. By the way, these are all off the internet. So I have to say that, you know, these are not pictures that I stole somewhere. I took them right off the internet. And I was hoping to find something like this so I wouldn't be accused of publishing something that I shouldn't have, okay? But I got to go from stem to stern on that. It was quite interesting. Another one. By the way, the first one I saw, there's a lot of this stuff along the side instead of the way we see it now. Other questions? Okay, to make a long story short, let me do one more thing here. Look at this round right there. This thing here turns 6 revolutions per minute. What do you think of that radar?
So wait, what part holds still and what part turns?
This whole dome. And there's a disc right there. That's the disc
Okay.
it turns on. Yeah, the whole
All
thing
right, that's the
turns.
pivot.
I used to think, in my ignorance, I used to think that the dome turned inside. But now I find out this whole thing rotates at 6 times a minute.
Huh.
So anyhow, besides anything else I want to go into tonight, I thought you guys would be interested in this. All right. Okay. Now let's get down to some of the let me do something else here. This was up in the Everett plant. I had another picture of where it was being done, but I couldn't find it. I lost it. And of course, yeah, then I have to show you this one. Oops. They overran the runway, didn't get stopped in time.
Oh,
Ouch.
ouch.
Yeah. I'll bet the guys in the cockpit, oh, gee willikers, right? But it's amazing what this was the Boeing 707, 737 that they modified and, is really build up the structure inside. So, like I said, it was pretty interesting. And by the way, on the classes that I taught, I got really good reports on that. There's always a follow-up. This is another really good one. Here you can see it is turning. It's a top view. By the way, all of these will be on the web just as soon as I can. So probably before next week is out. All right. This is a picture I showed a while ago, and that's the one that Barry was asking about. I am not really sure, but I have a suspicion that there's a lot of electronics there for navigation and possibly electronics with some look down. They always have a look down radar that sits right in here. By the way, when Air Force took it over, it was now called the E3. Yeah, so that's what home of the E3A. And you see a guard standing out here and it's roped off. So yeah, when the guys took me in, they took me in from the front, actually took me all the way to the back and then turned around and brought me up to the cockpit. So I got a good view of the whole thing. Well, anyhow, that was kind of exciting. The presentation tonight is actually one of over 20 different presentations, which goes into more detail than in the technology than what I'm going in tonight. All right, now let's do this. Here we go. First of all, in the manual, that is in the guide, this is the, see, I don't have it focused there. I guess I'll have to do it here. What do we got? Nope, gonna do it way back here. Anyhow, this is the Extra Class License Manual by ARRL. And the material I want to go into right now, it's probably pretty easy for most of you guys, but once in a while we get somebody that they run into it like a brick wall. I would like to clarify some things and also add some technology that's I used with these guys that's still not in the textbooks. For instance, let's do this. This is the kind of thing that they do. Now, first of all, these are called truth tables, as I'm sure everybody knows. What I'm going to do, though, and this is worth you guys writing down, there's 2 horrible things here. These are called mil-spec symbols. I hate them. I really do. Because when I'm teaching this in a classroom, These mil-spec symbols are a total obstruction to getting your head towards this and really understanding what's going on. What they want you to do, and this is what's going to happen in the test, they're going to say, okay, fill in the 0, 0, what's over here? Is this a 0 or is this a 1? And I call a 0 a low, and I call a 1 a high. This is the way it's been done for years and years. It's called an AND gate. And I'm going to say, that's nice, but let's do something else. All of these AND situations are functions. The mil-spec symbol does not show the function. It says they hope that the diagram will tell you everything you need to know. It doesn't. What we really have here is this. Instead of filling in these truth tables, notice that I have 2 lines and there are 4 possibilities. One of the problems with the truth table, and pay attention to this, if I add 1 line, all of a sudden I double the possibilities. This becomes ABC. And now I have not just 2 columns, but I have 3 columns, and it goes down for, guess what? Twice the number of 4, 8. 8 possibilities. Now suppose I add another line. Now I've got 4 lines. I'll have 4 columns, and this full thing will go clear down here to the bottom of the page because there are 16 different possibilities. Now if I add another line, so now I've got 5 lines. Oh my goodness, this thing jumped up. All of a sudden I have 32 possibilities with these lines over here. Okay, let's start with this. First of all, the truth table as they have it in, like if you take a test for the extra class. And by the way, there's one for the general class as well, just not quite as involved as the extra class, but I'm really covering both. Anyhow, what I want to point out is that this is an only gate. Only. Because there's only one time that gate will go active. And by the way, I'm not going to start, I'm also going to do something else. I'm going to stop calling it a gate and call it a device. There is a problem that we have today when you work with this stuff. You tend to think of everything in terms of chips. Don't do that. This is a function, and it is a function of a device. And there are many devices besides chips. In fact, when I taught the guys at the AWACS, chips did not exist yet. These symbols were not even put into motion yet. These are called mil-spec symbols. But when I taught the guys there, I taught functions of a device. Why? These chips didn't exist. So stop thinking of them as just chips. Let's go on to the next one. What they're really missing is this. There should be a dot to represent and. There should be a plus to represent or. Now let's do something else. I call this an only gate. That's my nickname. Why? Because the only time that this output will go active is when both A and, notice A and B are active. And when they're active, the gate goes active. And when it goes active, it drives the output high. Oh, there it is right there. Otherwise, if you don't have a high here and a high here, this gate here is low. You say, oh, well, it's resting low. In some cases, with some devices, it's actually driven low. But what I want you to see is that this represents a low, 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 and hey, there's the only time the gate goes active, high. Now down here on this one, NAND, even that I have problems with. That's a and not. Why? This guy here is called the not. An inverter is the not function. So it's kind of misleading to call it an and, like not and. Well, it is an and an only, because here we go. The only time this output will go high right there is when you have A high and B high. That's the only time that that output will go high. However, when that goes high, the process of an inverter is to invert the signal. It's kind of like called it electrical teeter-totter. If this is high, this is low. If this is low, this is high. It's an electrical teeter-totter. It inverts, and that's called the not function. Okay. Now, here's an interesting concept. I call these functions. These up here, we say, oh, these are gates. Oh, by the way, let's come back over here to this OR gate, as it's called. My nickname for this is called an any gate. Why? Because anytime A is high, oh, the gate goes active and the output goes high. Well, what about this one? Well, anytime A is high or B is high, or both of them, this output here is driven high. Bing, bing, bing. So when this is low, low, all of them low, the output here, the gate is not active, and this is low. Now, there's kind of an interesting thing, even though it's an any gate, because the output goes high anytime A is high or B is high. Guess what? There's only one time it doesn't. Let's begin to give a suspicious activity here that says, wait a minute, it's an any gate, and yet there's only one time. How about that? Well, I'll tell you what, let's do something else. Let's come back up here to this and now I'm going to throw another word in. This is a function. This device, notice I'm not calling it a chip. This device has an and for A and B. But suppose I come in here with a low. If I have a low, I just killed the gate. We'll have the funeral next week. Do you catch that? If that is low, you kill the gate. If B is low, you kill the gate. Somebody says, well, if I have a low here, what about this one? It doesn't matter. Whether you come in with a low here, which kills the gate, or you come in here with a low, which kills the gate, then that gate is totally non-functional. You're wasting your time following what's happening over here. You see that? So what I'm doing is I'm introducing two new terms. Here we go. If you put a high on this gate, that's a maybe. What do you mean maybe? Well, maybe it'll go active and maybe it won't. Well, I said a while ago that if A is high, that's a maybe. Now, what happens if B is high? That's a maybe by itself. However, if this is high and a high, now the gate goes active. But what about this? If I have a low, I kill the gate. That is forcing the gate. So the terminology that I use is called forcing versus maybe. And when you get this in your head and you start using it this way, there's a lot of circuit that just simply melts in terms of being able to mentally acquire what this is supposed to do. Now, is there a maybe condition over here? The answer is yeah. If I have a low, that's a maybe. If I have a low, that's a maybe. However, the two of them together create a low, all right? However, if I have a high, that's a forcing condition, because I don't care what you do with B. If you have a high, that forces the gate active, and you can do anything you want with B, but this guy here forces the gate active. So this forcing versus maybe is a thought process that really helps a person go through these, all right? Besides that, let's do something else. Truth tables, as I'm showing you here, are nice to prove something. But in the real world, nobody, when you're designing a circuit or troubleshooting a circuit, nobody uses the truth table. However, if you take the test, you're going to be looking at solving a truth table, okay? So what I'm showing you works without having to go through this 0, 0, 0, 1. How about down here? Oh, if this is a low, it kills the gate. This goes low, but this inverts high. Oh, that's where those ones come from. This low or this low or this low or this low, kill the gate. The output inverts to a high. The only time you get low then is when you have a high and a high, drives this high, which inverts to a low. Now, let's get into something else here. By the way, notice I did this in the early part of 1973. All right. I've used this for many, many years. In this particular case, I labeled it NOR, not as a NOR gate, but as a NOR function. Look at here, look at this truth table here, and it compares with this NOR function over here. So this NOR function here is replicated by an AND gate with two inputs as inverters. Watch what happens. A low and a low inverts to a high and a high, causing the gate to go active, driving the output high. And right there it is. However, if you put a high here, a high inverts to a low, which kills the gate. So whether you put a high here or a high here, either one of those, a high or a high or a high, it kills the gate. The output goes low, rests low. You see where we're going with this? Now, when I come down here to this one, and I have a few more mysteries to show you here, let's do it this way. This is a OR, but looks to me like suspiciously like that's a AND gate. Well, yes, it's an AND gate. However, if you take an AND gate and bubble input, and bubble the output, guess what happens? A low here and a low here inverts to a high here and a high here, which causes a high here, which inverts to a low. Oh, there it is right there. Now, there's something else. Did you notice that this guy down here, the truth table illustrates that this gate with bubble input, bubble output changes the function. Be careful about calling things by their gate, because a designer, and I have designed a lot of circuits, when you design a circuit, you never design it by the gates. You always design it by the function, always, all right? Now, suspiciously, I'm thinking, okay, if that's true on this side, maybe this is true. Yeah, sure enough. Here is a OR gate, if you want to call it that. But if you got bubble inputs, look what happens. A low here creates a high here, which is a forcing condition, and the output of the gate goes active high, bing, bing, bing. So this, a low here or a low here creates a high or a high. Therefore, the gate is active high, and there it is, there it is, and there it is. So the only time the gate goes low is what? When you have a high and a high, which creates a low and a low, the gate does not go active, and therefore the output goes low. You see where we're coming from? Now, what I'm really doing is I'm throwing some, let's call it some verbiage in here, that when you catch this verbiage, you'll find that trying to understand what these things do becomes just 1,000 times easier, okay? The technicians that I taught for the AWACS were able to go out and they could look at a circuit and know what it was doing because they were schooled on this concept. Now I'm going to show you something else. Watch this. Let's say that mentally I change everything. Watch what happens. No bubble, no bubble, no bubble, oh, or. Bingo. Right there. You see what I'm saying? You can do the same thing up here. You can say, if there's no bubble, put one in. No bubble, put one in. Change that to an AND gate and put a bubble out here. And guess what? That is the same thing as this. So in the books give a short paragraph or sentence on this. They call this De Morgan's Law. In the classroom, I've spent an entire day on this, drilling it into people until they finally get a comfortable handle on it. I'm going to throw something at you here. I call it Funk's Rule, or if you will, Dave Funk's Rule. If you change everything, you haven't changed anything. Try that again. Change everything. Bubble, bubble, and bubble. Oh, that becomes no bubble, or no bubble. That happens to be exactly what this guy is. You see where I'm coming from on this? So what I'm trying to say is stop thinking gates. Start thinking functions. And this is the reason why it's so important is because when I was doing all this, there were no chips. No chips. Everything was done by transistors. And by the way, negative logic as a general rule with PNP transistors that were where the circuits were transistors on a board. And I've got some boards from that time frame. When you make a circuit board today and you have a trace that goes from the top to the bottom, it goes through what we call a via. It means plate through holes. Plate through holes didn't exist when I was doing all this. When we look at things now, it's kind of hard to believe how many things have happened and how things have changed. It's amazing to me. Now, I want to point out something here. If you understand what I was talking about, you can look at a truth table and you can put one mark. When A and B are high, the output goes high, and you come down here, A and B high, put a mark for high, and guess what? All the rest of them are zeros. You can do the same thing with the NAND. Here again, I call it a NAND function. So if A is high and B is high, the two of them together drive the gate active high, which inverts to a low, and so you just go over here and put a low. Guess what? You've done the truth table with one mark. Now, obviously, if you're in a classroom and or passing a test, you'd have to fill in these others. You wouldn't put zeros up there. You'd put 1, 1, 1, 1. And the same thing is true over here with the OR gate. Guess what? When you have a 0, 0, in other words, low or low, the gate does not go active. And if it does not go active, this output here is active low. Bingo, right there. Then you fill in your 1, 1, 1. You see where I'm getting at on this? It is easy, once you understand the rationale of what I'm talking about here, you can mark a truth table in seconds instead of minutes. The NOT function used to be shown as an inverter, but this is not the best symbol. Sometimes there's a inverter with a bubble in the front or a bubble behind. More about that later, I guess. Oh, now let's get into something else. I heard somebody comment on the reflector about Boolean algebra. Boolean algebra is useful, and there are certain computer programs that you can use to design circuits without even looking at them like this. The dot is AND. So therefore, X1 out is A and B. Whereas over here, the plus represents a OR. That's what I do not like about the mil-spec symbols, is they have pulled these guys out, threw them away. They should never have done that. I do not like mil-spec symbols, as you can tell. Down here, let's do this one. Here is A and B with the bar. And when I said bar, there's the bar over both of them, and there's a dot in the middle. A and B bar. You say, what do you mean? A and B not is what that is. Come over here, look at this one. Y1, which is this guy here, and I didn't fill in any of the truth table, I'm only doing the Boolean. Y1 is A or B. Well, since it's the same thing down here, but with an inverter, it is A or B with a bar over both of them. Now, from what I saw the other day, I think there's a couple, 3 people that know Boolean algebra, and you would know this. This is rather interesting. I'll get down to these. Look what happens here. Here we have an A bar and a B bar. If you pull the bar across, so it becomes one like, oh, now you have to change the sign. So if you break the bar or meld the bar, you have to change the sign. Guess what that is? This is the same thing as A or B not. Guess what? That's what we found up here by doing the truth table. Let's take a look at this one. Y3 is A not or B not And you can extend the bar across to the two of them, making one bar. But if you do, you have to change the sign. This is useful. I know it may not look like that, but for people that are doing complex circuits, Boolean algebra follows many of the same rules that algebra does. Now, look at this one, A bar and B bar, but when it comes out of this, there's a bar over the bunch of them. So you break the bar, now you got A bar and a B bar, but guess what? They cancel. So the A bar cancels out to become just simply A, and the B bar becomes just B. Well, that proves by Boolean algebra that the function of this device, now notice I did not say gate, I said the function of this device is exactly the same as here, A or B. You can do the same thing over here on this guy. Y4 is A bar or B bar with a bar over the whole quantity, which does the same thing before, but you can break the bar, which leaves double bar, and the double bar, oh, they just cancel out. Oh, wait a minute here. We went from an or to a and. Therefore, this circuit here, the function of this device, notice I did say device, the function of this device is exactly the same as this device. Now, it's important to know this, and I'll tell you why. In the real world, you may have another device over here, which has a bubble on the output like this guy, feeding this, so this bubble here may not actually be here. The bubble may be over here in this other device, but you can mentally, notice what I'm saying here, you can actually do a little bit of a mental gymnastics here, if you want to call it that, and knowing that if this comes over like that and over like this, these bubbles can actually come from somewhere else. You may have a NOR gate, if you want to call it that, but the bubbles, you slide them over, and then all of a sudden you say, oh, wait a minute, this whole function changes. True story. At Clover Park, we had a 2-year waiting list, and we really drilled the students on all this. One of the students graduated, went back up to Alaska, got a job with Alaska Airlines, I believe it was. And of course, along with some other students, they put him into a room and gave him some test papers. And the student that graduated from our course, by the way, he really had a tough time holding in there. We had to hand him snorkel gear once in a while. But he looked at the circuit and he said, oh, and went and figured it all out. And the students around him said, how did you figure it out so fast? And the instructor happened to be walking by at the time and says, yeah, how did you do that so fast? He'd never heard of this. He said, well, I just looked at circuit and I slid this inverter over and then transformed the gate and I had the answer. He said, where did you learn that? So anyhow, this is really a very important function here. All right, so here's our final synopsis. This device has the same function as this device. This one here has the same function as this one. And this device here has the same function as this here. And this one here has the same function as this one here. You can prove it by truth tables, but you can also do what I showed you and get the same thing. How are we doing? Are you following me?
Yes.
Did I lose anybody? All right. I want to do something else here now. Short. I have some diagrams here that show how you can take inputs. Now, here's what's interesting. A gate, a multiple input gate, can be used for signal passing. I can have two different signals coming in here, and when they hit, this one here inverts before it hits the gate. So therefore, the output right here before that inverter is a coincidence gate of these two inputs. The gate itself, however, won't work unless you enable it. This guy here has to go on high. Here we have a bubble and a bubble. These are called inhibits. And when the inhibit goes high, that turns off the gate. It kills the gate. So in other words, you won't have a data stream. And now I'm talking about dynamic signal analysis. So what happens when you put all these signals together with enables and inhibits? Guess what? There's your dynamic output right there. The output is driven low when all these come about. I only have one more thing to show you. I'll take the time for that. In the book, when you look at the material for the test, they also talk about what's called cross-coupled NANDs. These are two, yeah, they're NAND gates. They're 7400s is the chip number. And by the way, all four of these are in one chip. All four of these are in one chip. These two here and these two here are in another chip. Now, this is a circuit that I came up with back in 1973 for my keyer, and it works. Here's what the book tells you, though. Watch this. If I come in here and I put a low, that kills the gate, right? However, does that mean it's dead in the water, doesn't do anything? No, here's what happens. If that guy there goes low, the output goes high. This now becomes a flip-flop. And as a flip-flop, it's very, very useful. It's used in circuits for debounce. When you have a relay or a push button, that fool thing can bounce 20 times. And as a result, there are certain circuits that can pick that up and really get upset trying to do things it's not supposed to do. So what people often do is they'll take something like this or come over here to this guy. When that switch goes down, it makes not one contact, but it might bounce several times, but it only takes one to make this guy here go into a flip condition. If I come in here and put a low here, it makes it go flop. So they call it a flip flop, okay? Now, here's where the book is wrong. The book says if you have a high here, that's a maybe, but what happens if you have it low, like that switch? That's low, and this is low. It's no longer a flip-flop. And what the books say is wrong, where they say, oh, now the outputs here and here are indeterminate. No, that's wrong. What they're really saying is, whichever guy lets loose, be it this one or be it this one, it will either go to a flip or to a flop.
It'll stay there.
Say again?
It'll stay there, yeah.
Yeah. However, what happens, let's come down here to this guy. I found an advantage. If this is low and this is low, this output will go high and this output will go high, both of them. And I said, that's exactly what I want, because here, this guy here says, I'm ready for whoever comes first. If I want to send a dit or a da, whoever gets there first, this thing here is ready for either one that comes in first. However, once one of them comes in and gets things going, it circles around here and tells, okay, let it go. And all of a sudden, this guy says, okay, he can't go now because we turned him off. Next turn. So like for iambic keying, when you squeeze both paddles, how does this thing alternate? Well, this thing here becomes a flip-flop, 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 depending on whether it does dits or das. However, when nobody's doing anything, it's sitting there and say, okay, first come, first serve. What do you think? It works, by the way, and this is, anybody can copy this, anybody can build it.
If you look at the chips.
By the way, there are some chips that are becoming impossible to find now, but these here are still readily available, In my curiosity for designs, I'm now up to 10 or more different versions, and I have never been able to improve on this design. Okay, questions? And otherwise, I'm done.